Hello, my name is Raed. I'm an assistant professor at the University of Michigan, and I'll be talking about personalized federated learning via domain adaptation. So I'll start by discussing the background on federated learning and then talk about personalized federated learning. The talk today is based on the paper Personalized Federated Learning via Domain Adaptation with Application to Distributed Manufacturing. This is a paper with my student Naichen, and it is published in Technometrics. So one needs to take a step back and understand first why there was this explosive interest in federated learning. And I do want to give this small background at the beginning. And really, the main reason is Internet of Things, IoT. Currently, the current system of IoT is a centralized one. For example, I'm at Michigan, and we have GM, we have Ford, we have their IoT systems where they collect data from cars on the road. If you subscribe to their systems like OnStar for GM, Sync for Ford, this data is uploaded to a cloud, and on the cloud, in this back office or the cloud, a lot of analysis is being done, models are being learned, like predictive maintenance, and the hope is to keep the driver informed about the health of their vehicle. But these big IoT giants have quickly realized that there are very fundamental drawbacks to this centralized approach where all the data is being uploaded to a central server. First of all, learning the models from such huge data being collected in real time can be very challenging, very energy consuming, and extremely expensive. Indeed, many of these companies will take subsets of the data and learn on smaller scale samples that are more clean, just to save on the cost and the energy expenses of learning these big models. And the expertise needed as well. And there is also this communication burden. Often the data is being collected with high frequency, and sending the data over in real time is very challenging, very time consuming, very costly. It consumes a lot of energy bandwidth. Storage is another problem. Storage comes with a cost, and the need to store all this data that is being uploaded with high frequency is very challenging. And there is also privacy concerns. Many users, the fact that they are sharing the data in real time, the fact that the companies know where they are located at any point of time will somehow discourage them from subscribing to these services. Okay, and there is this notion of a deployment latency in the sense that the user is always dependent on the cloud to do the analysis and send back the decisions. If there is this latency, then the user cannot do anything. They need to wait for the decision from the cloud to be sent to them. So really, the federated learning was a result of a fundamental change in IoT, which is very simple. The computational power of the edge is rapidly increasing. For example, Tesla just posted that on the car itself, there is compute power equivalent to a few MacBook Pros on the car. AI chips have become much more expensive than before. Raspberry Pis were a few $1,000. Right now, you can get a very good Raspberry Pi with $100. And we are all working with very powerful AI chips, our smartphones. And this is why this increase in the compute power at the edge really was the key reason behind federated learning. Why? The idea of FL is very simple. It is that by exploiting the compute resources at the edge, we can process more of our data where it is created, at the edge. And this is why IoT can move from the cloud to the crowd. This is the promise of federated learning. To take a very simple example, let's assume we have a central orchestrator, say Google, and Google wants to learn an average of some feature over all the clients. If the clients do not have compute power, then every client needs to send their entire feature vector. But if each client has some compute resources, then they can calculate locally their mean and send their mean and the data size, and those are sufficient statistics for Google to learn basically the average over all the clients. Okay, this is but one simple example showcasing that less data is transmitted, okay, less information is stored at the edge, and still the analysis and the statistical results are pretty much the same. In reality, when we are learning bigger models, more complex models like deep neural networks, the process becomes iterative between the global server and the clients. But this is but one simple example. And why this is important, one reason clearly is privacy. By sharing summary statistics, you're sharing much less data. And at the same time, it's much easier to encrypt summary statistics compared to encrypting entire data sets. Also, computation and energy, clearly, a lot of parallelization is happening in the computational power. This is a big benefit actually for the companies, because for these big companies right now are using the computational power on your laptops, on your phones, instead of using their own computational powers. They're using something you paid for, the users. There is also cost benefit. Less information is transmitted, less storage, less bandwidth expenditures. And finally, there is fast alerts and decisions in the sense that if you have an Apple Watch and you have a model on hand, the Apple Watch can do the decision locally. It doesn't need to wait for a central server anymore. Okay. Here in federated learning, most of the literature, since its explosive interest in 2017, has been on this notion of global modeling. And here I call the global model as one model that fits all. For example, if I'm learning an X word prediction model, I'm learning this big model for all my users. Okay, it's one model for everyone, one neural network for everyone. And let's set the mathematical notation first. Let's assume we have n clients, okay, and phones and patients and users. And the goal of federated data analytics or federated learning is that we want to collaboratively learn some model, f of w. This can be a linear model or a deep neural network, and it is parameterized by the parameters w, weights of a neural network, for example. And often when you have distributed data, the objective is that we want to minimize the average risk. F of W is the average risk. So you can see it's the average over all the local clients' risk. I is an index for client I, and we're trying to minimize the risk in expectation over all the clients. P is here is some weight. It can be simply 1 over n, just equal weights for all clients. And the risk function is a function where we take the expectation over the data over some loss function for the model. So the loss function, if f of w, if we are doing a classification task, can be cross entropy, or doing regression mean squared error, and in reality, we do approximate our risk functions via the empirical risk, just the average over the data that we have. And the key challenge in federated learning is the clients cannot observe each other's risk because they do not observe the data from other clients. At the same time, the central server cannot observe any risk, cannot evaluate any risk at any point because they do not have any data from the clients. So how does learning occur? In general, learning takes 2 general steps. The first step is the orchestrator will send the weight W to all the clients. The clients will receive W, do some local updates, the client update, and then send back this W, and the orchestrator will just aggregate. So it's a 2-step procedure where there is it's W being sent, everyone does their updates, then there is the aggregation that happens in the orchestrator's level. Okay. And indeed, one of the most popular and still to this day powerful algorithm that really initiated this explosive interest in FL is called federated averaging. It's very simple. The client update is simply gradient descent. Every client does a few steps of gradient or stochastic gradient descent. And then the orchestrator simply takes a weighted average. That's it. But people quickly realize that this approach has fundamental challenges, specifically when there is heterogeneity. When the distribution of the data across different clients is slightly different, then this approach of learning a global model can directly and easily fail. And people have observed that empirically. And the fundamental reason is the optimal solution of the expected risk is not the same as the optimal solution of every client's risk. It's not those two. If you take the average of those two, those are not equal. Because heterogeneity, basically, every client can push the model in their direction. And this heterogeneity, even in homogeneous cases, can happen. Because if you look at the theory of FL, the theory will tell you that the number of local steps cannot be a lot. Because even if things are homogeneous and you do many local steps, every client can push their model in their direction, different directions, simply because of stochasticity of the gradient descent of the data of the noise. And then taking the average may not make sense. So the solution that people proposed was personalization. Basically, instead of having all of them red circles, everyone has the same model. Let's allow collaboration, but eventually every client retains their own individualized model. And really, the general model is we're still minimizing the expected risk, but here we're trying to optimize over 2 parameters, W, which are a set of shared parameters, and theta I, which is a set of unique parameters for every client I. So every client is gaining their own set of unique parameters, theta I here. And really, 2 approaches are most dominant in literature. The first one is weight sharing, and the second one is regularization. In the weight sharing, it's more specific to neural networks where somehow the first few or the last few layers, often it's the first few, are global. Those are the parameters that are shared across all the clients. And the last few layers, the weights of the last few layers are local. And collaboration happens, or federated averaging or federated learning happens only to learn the global parameters, and every client does updates for the local or unique parameters based on their own data alone. Okay. The other approach, which is based on regularization, is more of a trained and personalized approach. In the sense, we first of all collaborate to learn a global model W star. This is one model, the big model for everyone. And then each client uses their own data to fine-tune W. Here, by fine-tuning, it means let's get our unique parameters data I, but make sure that our unique parameters are within some ball or are close to this global parameter so that we retain global knowledge. And this can be done using a proximal term here, Fisher information penalty. And there is also some literature recently, and we will compare with one called DITO, where this is done iteratively between learning the global model and personalizing it. Okay. Unfortunately, this literature can easily fail this approach to personalization. Let me give you a simple example before justifying why. Let's take an example where all the functions across different clients I are simply sinusoidal functions with a phase shift. This is very common in engineering systems with vibration signals. In this situation, if you if you assume U is uniformly distributed on 0, 1, you can prove that if you minimize the population risk over all the potential clients. The optimal solution is simply a straight line, is any function where the prediction is 0. It's a straight line. And what then? Some approaches that say train them personalized. So if you have heterogeneity, that means the global model can make no sense. So you're personalizing on a model that makes no sense. You're getting nothing. Okay? There is a fundamental problem here. And what is the fundamental problem? It is the fact that in heterogeneity is a function of the joint distribution of X and Y. When we say let's model the functions across different clients as having different parameters, basically we're saying we want the input-output relationship across different clients to vary. And fundamentally, what we are saying is we want to model a change in the conditional distribution of Y given X. Okay? This is what literature is doing. But in reality, the distribution of X can also be different. The input distribution can be different across clients, and this is often called a covariate shift. For example, if some clients have a different style of writing, or some clients' cars are operating in hot weather, then the temperature distribution as an input can be different across those clients. So any approach to heterogeneity should tackle both sources of heterogeneity. And really, if you look at this example, you can see that somehow if you see at X, there's the distribution of the probability of X, the marginal distribution of X is indeed different across the clients. It's shifted. So our approach is to solve this problem is through domain adaptation. Okay, let me dive deeper on what we mean by domain adaptation, but let me show you our general model. Our model, instead of learning one mapping, a single big mapping parameterized by some parameter W or theta I, we say, okay, let's learn a composite mapping, where the first part of this composite mapping, phi parameterized by beta I, is an encoder that takes input X from different clients and maps them, hopefully to a domain invariant space. So brings all the different distribution, the marginal distributions of X across all the clients into one joint distribution so that all of them have the same marginal distribution. And then a decoder, where given that everything has the same marginal input distribution, we can take it back to the output. We can decode it, okay? So phi is the decoder parameterized by beta, and G is the encoder parameterized by gamma. And here, for the sake of generality, I assume they can be any functions. If you're doing neural networks, they can be both parameterized by neural networks. You can parameterize them by linear models. This is just a generic model. So but one cannot just simply say, okay, let me use this model and let me minimize the average risk over all the clients given this model and optimize over gamma and beta. How can you guarantee that or how can you encourage your model to have domain invariant features? Because without having domain invariant features, you cannot learn well under heterogeneity. So our trick to solve this problem is using bi-level optimization. And what I want you to take from this slide is two things. First of all, remember the model right now has two parameters, gamma I and beta I. Here we introduce a dummy variable, W. Okay, which we discussed before, but here we'll treat it as just a dummy variable, W. And again, the model has two levels. In the lower level, we are trying to minimize the average risk, and FI is just the risk function of each client using the dummy variable. And the upper level, we're trying to minimize a regularized risk. This is not the risk for each client, but rather the risk with some regularization. So those two things I want you to remember is first, we're adding a dummy variable W. And we also have in the upper level on the of the optimization a new risk function. It's a regularized risk function. So let's dig deeper into each part. So for the lower level, you can see what we're doing just like what federated averaging or federated learning is doing. It's minimizing the average risk over all the clients. But we're learning this beta I, which is the decoder's individualized parameters, and we're learning the dummy variable W, which is the parameter parameterizing the decoder. The most important part here is the following. It is that somehow it's that our model has a single decoder for all the encoders. So the encoders are flexible, but we have a single decoder. So we are forcing the model in the lower level of the optimization. We're forcing all the input X over different clients. You can be mapped over different betas to this feature space, but all of you should be mapped by a single decoder to your output space. So by forcing all the encoders to be decoded using a single decoder, we're forcing them, we're encouraging them to come, all the X's to come to a domain invariant space. Because if they come to different spaces, they cannot be mapped back by a single decoder. This is the fundamental trick of using W as a dummy variable. And then, right now, we have a domain invariant space. Then we can use the tricks in personalization or the regularized personalization where we say, okay, now let's learn gamma I, the personalized decoder, to handle for the input-output relationship change, the concept shift, but make sure to be close to this global decoder. This is a simple and fundamental trick. And it turns out learning this model is very simple as well. It doesn't need a lot of changes compared to traditional approaches. Basically, we're learning the encoder parameters and this dummy variable by updating the local risk, and the gamma I, which is the personalization parameter for the concept shift, using the regularized terms. And the only thing that needs to be shared between the clients and the server is this W variable, the dummy variable. Okay. The algorithm is rather simple, so I will skip it here. And it turns out that our method has good theoretical guarantees. Here, under non-convex settings, under regular assumptions like Lipschitz continuity, we can show that our parameters W and beta, the dummy variable and beta, which is for the encoders, converge at log t over root t, which are regular rates for federated learning. However, the gamma I, which is the personalization, gamma I, converges at slightly lower rates. This is due to the bi-level configuration here, and it's a price to pay for personalization in general. So it converges at slightly lower rates. This is an example where we have three sign functions, going back to the example that motivated this problem. We have three sign functions, and each function just has 5 data points. And we use individual learning. Okay, we use individual learning. And you can see, obviously, the individual learning doesn't work well because we have very few data to learn. It's a good enough model. For example, in this situation here, for the blue line, the model just learns a straight line. Our approach, personalized federated learning via domain adaptation, does extremely well. And we also compare with a personalization approach that does not account for domain adaptation here called D2. It's one of the state of the art. And one interesting thing to see here is our encoder. You can see the encoder, although there are differences in the functions, brought the input to a domain invariant space. You can see the domain of all the input has been brought together. And actually, one interesting thing is if we revisit the initial example, and we assume that all the functions are generated by U is uniform on 0, 1, alpha is normal with mean mu alpha, and the sinusoidal functions. So those are sinusoidal functions with phase shifts. And if we parameterize the model correctly, so we parameterize X as having just this phase shift, and the decoder as being a sinusoidal function, okay, we can actually show that the optimal decoder, okay, that we learned, the optimal single decoder g of w, so the w being learned, takes the form of mu a assigned to alpha, and mu a is just the mean of alpha. So basically, this dummy decoder that we have, the single decoder that maps everything, can be seen as a center over all the decoders. It's the average decoder, mu I, which is the mean of alpha. And then when we want to do the personalization with gamma I becomes a weighted combination of the actual true parameter and this mean decoder. And this is reminiscent of indeed Bayesian theory, where somehow the dummy variable behaves as a prior, and this is the posterior. And you can see the posterior is a combination between the truth and the mu alpha, and lambda 1 is the regularization. So if there is no regularization in our model, we do not encourage the W to be close to gamma I, then this will be just simply alpha I. Okay, so this is reminiscent of Bayesian theory, and just it's a proof of concept how our method works. And indeed, we did some testing on different data sets. In the paper, there are multiple data sets that we test on. You can see that the common theme across the different data sets is that the data across different clients may have some shift in the input. For example, here we have figures of giraffes, but we have different styles: real figure, drawing, cartoon, animation. And we indeed find that our model achieves state of the art. And we also do a nice engineering example with our collaborators here at Michigan, where we had multiple 3D printers, and we were trying to learn the mapping between acceleration and speed. This is an important mapping because it dictates the defects in in whatever you print. And the interesting thing is all the printers were of the same kind and make, and they were printing the exact same thing. It was a cube, okay? Yet there were a lot of differences between the printers. And what we believe the differences are simply because of how the printers were assembled, because they do not come assembled. And if you simply somehow fix the nods a lot or tighten them a lot, the differences in how much you tighten the knots will lead to big differences in the acceleration and speed. Not big differences, but there are fundamental differences. This goes back why it's important to model uncertainty. Here, the functions are not that complicated, so we use we parameterize our decoder and encoders, sigmoid, Gaussian network, also neural Gaussian models, also neural networks, and indeed we find the benefits of addressing domain adaptation and personalization and our model compared to what exists. Okay. Thank you.